Welcome everyone. Today we'll explore degradation threats to the oil process and produced water systems. An overview of threats and mitigation strategies in oil and water treatment systems. This presentation will cover key process stages, internal and external threats, and mitigation strategies. Introduction. This presentation explores degradation threats in oil processing and produced water systems. It highlights key process stages, internal and external threats, and mitigation strategies. This diagram illustrates the overall process flow of oil and produced water systems. Each stage is vulnerable to specific degradation threats, which we'll examine in detail. This diagram refers to Corrosion Threats Handbook, Upstream Oil and Gas Production Plant by Energy Institute. Process Flow Overview. In the separation stage, threats include corrosion from water and CO2, and fouling due to solids. Monitoring pH and using corrosion inhibitors are common practices here. From downhole to surface, three-phase fluid journey. During the heating and treatment stage, scaling and thermal degradation are common. Anti-scalants and temperature control systems help mitigate these issues. Number 1 of three-phase fluid journey is starting from downhole or subsurface. Fluids, oil, gas, water, are produced from the reservoir. May include downhole separation such as water separated and re-injected. Artificial lift systems such as electric submersible pump or ESP and gas lift help bring fluids to surface. Number 2 of three-phase fluid journey after downhole or subsurface is wellhead, interface between downhole and surface, controls pressure and flow. Number 3 of three-phase fluid journey after wellhead is inlet to surface facilities. Three-phase fluids enter separation systems, primary separator, separates gas, oil, and water, heater treater or free water knockout, further separates water, produced water treatment, removes oil from water before discharge or re-injection. Downhole internal threats to be considered. Number 1 is carbon dioxide corrosion or CO2. This occurs when CO2 dissolves in water to form carbonic acid, which aggressively attacks steel. It's common in production environments with high CO2 content and can lead to uniform or localized corrosion. Number 2 is hydrogen sulfide corrosion or H2S, also known as sour corrosion. H2S reacts with iron to form iron sulfide and hydrogen. The hydrogen can cause embrittlement, leading to cracking, especially in high-strength steels. Number 3 is microbially influenced corrosion or MIC, caused by bacteria such as sulfate-reducing bacteria or SRB. MIC accelerates corrosion by producing corrosive byproducts like hydrogen sulfide or organic acids. Number 4 is galvanic corrosion, occurs when two dissimilar metals are electrically connected in a corrosive environment. The more anodic metal corrodes faster, which can be a concern in mixed metal completions. Number 5 is weld corrosion. Welded areas can have different microstructures and residual stresses, making them more susceptible to localized corrosion, especially if not properly treated or inspected. Number 6 is grooving corrosion, a form of localized corrosion that occurs along weld toes or crevices, often due to flow disturbances or deposits that create differential aeration cells. Number 7 is crevice corrosion, happens in shielded areas like gaskets, flanges, or under deposits where stagnant fluid allows aggressive ions to concentrate, leading to rapid localized attack. Number 8 is stress corrosion cracking or SCC, a dangerous form of corrosion that combines tensile stress and a corrosive environment, leading to sudden and brittle failure without significant deformation. Number 9 is erosion, caused by high-velocity fluid or solid particles impacting the pipe wall, leading to material loss. Common in high-flow or sand-producing wells. Number 10 is erosion corrosion, a synergistic effect where mechanical erosion and chemical corrosion work together, accelerating material degradation, especially in turbulent flow areas. Number 11 is external corrosion. While not internal, it's worth noting that external corrosion can affect downhole equipment, especially in poorly cemented or waterlogged annuli. Number 12 is miscellaneous acid corrosion, refers to corrosion caused by acidizing treatments or naturally occurring organic/inorganic acids in the formation. Proper material selection is key to mitigation. Downhole external threats to be considered. Number 1 is external corrosion. This type of corrosion occurs on the outer surface of downhole tubulars and equipment. It is typically caused by contact with corrosive formation fluids, groundwater, or poor cement isolation. Factors such as CO2, H2S, and oxygen ingress can accelerate the corrosion rate. Proper casing design, cementing, and use of coatings or cathodic protection are key mitigation strategies. Number 2 is fatigue and fretting. Fatigue refers to the progressive weakening of materials due to cyclic loading, such as pressure fluctuations or tubing movement during production and injection cycles. Fretting occurs when two contacting surfaces experience repeated relative motion, leading to surface damage and crack initiation. These mechanisms are especially critical in deviated or dynamic wells and can lead to premature failure if not properly addressed through design and inspection. First stage separator, initial separation of oil, gas, and water. Subject to corrosion and scaling. Topsides internal threats to be considered. Number 1 is water-wet hydrocarbon fluids. These are hydrocarbon fluids that contain free or emulsified water. The presence of water increases the risk of internal corrosion, especially when combined with corrosive gases like CO2 or H2S. Water-wet conditions can also promote microbial growth and localized corrosion. Number 2 is carbon dioxide corrosion or CO2. CO2 dissolves in water to form carbonic acid, which is corrosive to carbon steel. This is a common threat in topside piping and vessels handling wet gas or condensate streams. Number 3 is hydrogen sulfide corrosion or H2S. H2S can lead to sour service corrosion and hydrogen-induced cracking. It's especially dangerous in wet environments and requires careful material selection and monitoring. Number 4 is oxygen corrosion or O2. Oxygen is a highly aggressive oxidizer. Even small amounts of oxygen ingress can cause rapid corrosion, particularly in systems that are otherwise anaerobic. This is often a concern in storage tanks and during shutdowns. Number 5 is microbially influenced corrosion or MIC, caused by bacteria such as sulfate-reducing bacteria or SRB. MIC can lead to pitting and localized corrosion. It's often found in stagnant or low-flow areas where biofilms can develop. Number 6 is galvanic corrosion, occurs when dissimilar metals are electrically connected in a conductive fluid. The more anodic metal corrodes faster. This is a concern in mixed metal piping systems or where clamps and supports are made of different materials. Number 7 is weld corrosion. Welded joints can be more susceptible to corrosion due to differences in microstructure and residual stress. Poor welding practices or lack of post-weld treatment can exacerbate this issue. Number 8 is grooving corrosion, a localized form of corrosion that occurs along weld toes or at the interface between different materials. It's often driven by flow turbulence or deposits that create differential aeration. Number 9 is crevice corrosion, happens in tight gaps or shielded areas where fluid becomes stagnant. Oxygen depletion in these areas leads to aggressive localized attack, often under gaskets, flanges, or deposits. Number 10 is stress corrosion cracking or SCC, a combination of tensile stress and a corrosive environment can lead to cracking. This is particularly dangerous because it can occur without significant warning or visible damage. Number 11 is erosion. Caused by high-velocity fluids or entrained solids impacting the internal surfaces of piping and equipment. This leads to material loss and thinning, especially at bends or restrictions. Number 12 is erosion corrosion, a combined effect of mechanical erosion and chemical corrosion. The protective film on metal surfaces is removed by flow, exposing fresh metal to corrosive attack. Number 13 is miscellaneous acid corrosion, refers to corrosion caused by organic or inorganic acids, either from process fluids or cleaning chemicals. Proper neutralization and flushing procedures are essential to prevent damage. Hydrocyclones, used for water treatment. Vulnerable to erosion and fouling, produced water treatment faces biological fouling and chemical scaling. Biocides and filtration systems are used to maintain system integrity. Degradation removes dissolved gases. Susceptible to internal corrosion, external threats include environmental factors like temperature fluctuations and humidity, which can accelerate corrosion. Protective coatings and insulation are used to counteract these. Water treatment. Number 1 of water treatment is second stage separator. Number 2 of water treatment is third stage separation or coalescer. Both process includes filtration and chemical treatment. Threats include biofouling and scaling. Internal threats stem from process fluids and contaminants. These include chemical reactions, microbial activity, and abrasive particles. Regular inspection and chemical treatment are key. Water treatment, stage 2 and 3 inch. Let's focusing on the third stage separation or coalescer and associated threats. Number 1 is third stage separation or coalescer. This stage is designed to further separate water from hydrocarbons after the second stage separator. The coalescer promotes the merging of small water droplets into larger ones, making them easier to remove. This improves the quality of the treated water before disposal or reinjection. Number 2 is filtration and chemical treatment. Both the second and third stages typically include filtration units to remove solids and chemical dosing systems to aid in separation, prevent scaling, and control microbial growth. Common chemicals include demulsifiers, scale inhibitors, and biocides. Number 3 is threats, biofouling and scaling. Biofouling occurs when microbial colonies form biofilms on internal surfaces, reducing efficiency and potentially leading to corrosion. Scaling is the deposition of mineral salts, such as calcium carbonate or barium sulfate, which can clog equipment and reduce flow capacity. Number 4 is internal threats from process fluids and contaminants. These include chemical reactions between treatment chemicals and process fluids, which can lead to corrosion or fouling, microbial activity, especially in stagnant zones, leading to microbially influenced corrosion. Abrasive particles, sand or solids can erode internal surfaces, especially in high-velocity areas. Water treatment external threats to be considered. Number 1 is external corrosion. This is corrosion that occurs on the outer surfaces of water treatment equipment and piping due to exposure to the surrounding environment. Factors such as humidity, rain, salt-laden air, especially offshore, and chemical spills can accelerate corrosion. Protective coatings, regular maintenance, and environmental monitoring are essential to mitigate this threat. Number 2 is corrosion under insulation or CUI. CUI is a hidden and often underestimated threat. It happens when water penetrates the insulation and becomes trapped against the metal surface, leading to corrosion that is difficult to detect without removing the insulation. This is especially problematic in hot or humid environments. Preventive measures include using water-resistant insulation materials, sealing insulation properly, and conducting periodic inspections. Number 3 is fatigue and fretting. Fatigue occurs due to repeated mechanical stress or vibration over time, which can cause cracks and eventual failure, particularly in welded joints or structural supports. Fretting is caused by small, repetitive movements between two contacting surfaces, leading to surface wear and potential crack initiation. These threats are common in vibrating equipment or piping systems and require proper support design, vibration dampening, and routine inspection to prevent failure. Injection pump, pumps treated water back into reservoir. High risk of erosion and mechanical wear. This slide defines the abbreviations used in the diagram, such as MIC for microbiologically influenced corrosion and EAC for environmentally assisted cracking. What, where, when and how to focus on injection pump. Number 1 is function. Pumps treated water back into reservoir. The injection pump plays a critical role in the water management system. It pressurizes and injects the treated water into the reservoir, either for disposal or for maintaining reservoir pressure in enhanced oil recovery operations. The pump must handle high volumes and pressures consistently. Number 2 is high risk of erosion. Erosion is a major concern due to the presence of fine solids or sand particles in the treated water. These particles can impact internal surfaces at high velocity, gradually wearing down impellers, casings, and seals. This can reduce efficiency and lead to premature failure. Number 3 is mechanical wear. Continuous operation under high pressure and flow conditions causes mechanical stress on moving parts. Bearings, seals, and shafts are particularly vulnerable. Vibration, misalignment, and cavitation can accelerate wear and reduce pump lifespan. Number 4 is mitigation strategies, use of erosion-resistant materials and coatings, installation of effective filtration systems upstream, regular maintenance and condition monitoring, e.g., vibration analysis, pressure checks, ensuring proper alignment and operating within design limits. Injection well, final stage for water disposal or reinjection. Downhole corrosion and scaling are common. Injection well is a final stage for water disposal or reinjection. The injection well is the last step in the produced water treatment process. After separation and treatment, the water is either disposed of into a designated formation or re-injected for pressure maintenance or enhanced oil recovery. This process must comply with environmental and reservoir management standards. Internal and external threats. Topsides threats include corrosion, erosion, scaling, and fouling. Downhole threats include microbial-induced corrosion, scale deposition, and chemical degradation. In conclusion, understanding and mitigating degradation threats is essential for operational efficiency and safety. Threat types and abbreviations: CO for corrosion, ER for erosion, SC for scaling, FO for fouling, MIC for microbial-induced corrosion, and CD for chemical degradation. Mitigation strategies. Number 1, regular inspection and monitoring, advanced corrosion monitoring sensors. Number 2, use of corrosion inhibitors and biocides. Number 3, use of smart coatings that self-heal. Number 4, material selection and protective coatings. Number 5, predictive maintenance using AI analytics. Number 6, enhanced filtration, chemical dosing and separation technologies. Number 7, flow assurance and system design optimization. Number 8, real-time water chemistry. Monitoring. Number 9, operator training and digital twins for simulation. And, number 10, redundant safety systems and emergency protocols. Conclusion. Understanding degradation threats is essential for maintaining system integrity and performance. Proactive mitigation strategies can significantly reduce operational risks and costs. Thank you.